Welcome in the fourth section of our course. In this section, we'll be looking at the topic of dimensionality reductions and recommendation engines. Firstly, we'll start from dimensionality reduction using singular value decomposition. Next, we'll build recommendation engine in Spark using collaborative filtering. Next, we'll be using that recommendation engine to get top recommendations. We'll see the difference between dense and sparse vectors, and also we'll be looking at the label points and other data types. And this is a first video in which we'll be looking at the dimensionality reduction using singular value decomposition. So we'll be understanding SVD, we'll be using SVD from Spark, and also we will see an example test case of SVD. So let's look at the SVD. There is a test that we should reduce dimensions using SVD. We have an input data of vectors. First vector is a sparse one, and it has 5 elements, and sequence of 1, 1.0, 3, 7.0. Rest of elements are zeros, so index 2, index 4, and 0 will be equal to 0 as well. Next, dense vectors with first value equal to 0, and other values, subsequent values 0.0, 3, 4, and 5. All values are floating point numbers. Last vector is with first value 4.0 and then 2 zeros and 6 and 7. Once we have our data, we need to create RDD out of it. We are using parallelize method on Spark context to create an RDD of vector. Once we have that, we need to create a matrix. Matrix is an input for our SVD. SVD is working on the matrix. So we can see that it will be a matrix of 3 rows and 5 columns, because every vector inside our input has 5 elements. So 3 on 5. Once we have our matrix created, we can use a singular value decomposition. On the matrix, we can call compute SVD. Parameter is 5, so this is a number of elements that our matrix has, and also we need to specify if you want to compute the U factor of matrix. Returning result is singular value decomposition of row matrix and matrix. We can extract U, S, and V from our SVD algorithm. First matrix is U. It is a U factor of our matrix. Next is an S. Its singular values are stored in a local dense vector. Lastly is the V vector, and it is also a local dense matrix. So let's start this test and see the output of it. We can see that we printed out those 3 matrices, and it means that we were able to present our dense vectors as the SVD. It is very common algorithm for presenting really huge matrix via the 3 smaller ones.